Roger Joseph Boscovich, a name perhaps less familiar to the modern ear than his contemporaries, stands as a towering figure in the annals of physics and philosophy. His magnum opus, published in 1758, though bearing the imprint of 1757, Theoria Philosophiae Naturalis Redacta ad unicam legem virium in natura existentium, or Theory of Natural Philosophy, reduced to a single law of the forces existing in nature, represents a profound and audacious attempt to unify all physical phenomena under a single, elegant principle. To understand the magnitude of Boscovich's undertaking, one must first appreciate the intellectual climate of the mid-18th century. Newtonian mechanics held sway, having brilliantly explained celestial motions and terrestrial physics through the concept of universal gravitation. However, several phenomena remained stubbornly outside its grasp: cohesion, elasticity, chemical reactions, and the very nature of matter itself posed significant challenges. Scientists grappled with understanding these forces at short distances. When Newtonian gravitation appeared in Boscovich's work emerged as a direct response to these limitations. He sought a more fundamental explanation, diverging from the prevailing atomistic view of matter, which posited solid, impenetrable particles interacting through forces. Instead, he proposed a radical alternative: matter consists of indivisible points, devoid of extension, interacting through a single, universal force law that varies with distance. This force, repulsive at very short distances and attractive at larger distances, explains both the solidity of matter and the phenomena of cohesion and gravitation. The repulsive force prevents these points from collapsing upon one another, providing the basis for tangible objects. At greater distances, the attractive force mimics Newtonian gravity, accounting for astronomical phenomena. At intermediate ranges, there are alternating regions of attraction and repulsion. This is perhaps the most ingenious element of his theory, for it accounts for a wide variety of physical phenomena. Consider the collision of two billiard balls. Within the standard Newtonian framework, one might depict the collision as an interaction between solid spheres. Boscovich's theory offers a markedly different perspective. As the two billiard balls approach, their constituent point particles begin to interact through the universal force. The repulsive force at exceedingly close proximity prevents the points from merging. This gives rise to the observed solidity and elasticity. At larger distances, as the billiard balls separate, the attractive force contributes to the overall interaction, causing them to recoil from one another. Similarly, Boscovich explained elasticity by noting that if a point is displaced from its equilibrium position, the universal law dictates that harmonic oscillations occur naturally around the equilibrium point. Boscovich's law possesses a mathematical description, though he expressed it primarily through a graphical depiction rather than an explicit equation. The graph exhibits several key features. At extremely small distances, the force becomes infinitely repulsive, preventing points from coinciding. As the distance increases, the force transitions to attractive, reaching a maximum before decreasing to zero. Subsequently, the force oscillates between attractive and repulsive regions, with the amplitude of these oscillations diminishing as the distance grows. At larger distances, the force approaches Newtonian gravitation, following an inverse square law. Because Boscovich's law is a universal law, it governs interactions between all points in nature. One can immediately recognize its impact on understanding the diversity of materials. The precise arrangement of equilibrium points influences the properties of these materials. The immediate impact of Boscovich's theory was complex. It garnered considerable attention and admiration from some quarters, while facing skepticism and resistance from others. His contemporaries, accustomed to the concrete imagery of Newtonian particles, struggled to grasp the abstract nature of his point particles devoid of extension. The concept of an oscillating force, repulsive at some distances and attractive at others, appeared counterintuitive to many. The lack of an explicit mathematical formulation of the force law also hindered its widespread acceptance and utilization. Despite these challenges, Boscovich's ideas profoundly influenced subsequent generations of scientists and philosophers. One individual deeply impacted by Boscovich's theory was Michael Faraday. Faraday's concept of lines of force, which permeate space and mediate interactions between charged particles, bears a striking resemblance to Boscovich's vision of a universal force field. Although Faraday did not explicitly acknowledge Boscovich's influence, historians of science have noted the parallels between their ideas. Faraday's work, in turn, laid the foundation for James Clerk Maxwell's electromagnetic theory, which unified electricity, magnetism, and light. One might argue that Boscovich's concept of force fields played an indirect role in the development of electromagnetism. Another notable figure influenced by Boscovich was Lord Kelvin. Kelvin, a staunch advocate of mechanical models in physics, initially found Boscovich's abstract point particles difficult to accept. However, he later recognized the potential of Boscovich's ideas for explaining the properties of matter. Kelvin explored the possibility of constructing mechanical models that would mimic the behavior of Boscovichian point particles, leading to his vortex atom theory. While Kelvin's vortex atom theory ultimately proved unsuccessful, it demonstrated the enduring influence of Boscovich's ideas on 19th-century physics. The development of quantum mechanics in the 20th century provided a new perspective on Boscovich's theory. Quantum mechanics, with its emphasis on wave-particle duality and probabilistic descriptions of nature, challenged the classical notion of point particles. However, quantum field theory, which describes fundamental particles as excitations of quantum fields, bears a conceptual resemblance to Boscovich's vision of a universal force field. In quantum field theory, interactions between particles are mediated by the exchange of force-carrying particles, such as photons and gluons. One might interpret these force-carrying particles as manifestations of Boscovich's universal force law. Erwin Schrödinger, the father of wave mechanics, admired Boscovich's theory of natural philosophy. Schrödinger had a copy of Boscovich's book in his personal library. Schrödinger wrote about Boscovich's influence on his own thinking about atomic theory. For example, Schrödinger referenced Boscovich in his 1951 book, Science and Humanism. Schrödinger highlights Boscovich's departure from the typical atomistic ideas of his time and his anticipation of field theories. Another testament to Boscovich's forward-thinking nature is exemplified in his contributions to non-Euclidean geometry. Boscovich made contributions to mathematics and geodesy. In his work on determining the shape of the Earth, he confronted the limitations of Euclidean geometry when dealing with large-scale measurements on curved surfaces. This foreshadowed the later development of non-Euclidean geometries by mathematicians such as Gauss, Riemann, and Lobachevsky. Critiques of Boscovich's theory centered around its abstract nature and lack of experimental verification. Critics argued that point particles devoid of extension were metaphysical abstractions, lacking any physical reality. The absence of an explicit mathematical formulation of the force law made it difficult to test the theory experimentally. These criticisms, while valid in their time, reflected the limitations of the prevailing scientific understanding. Boscovich's ideas were decades ahead of their time, anticipating concepts that would only be fully developed in later centuries. In more recent times, the advent of computational physics allowed scientists to revisit Boscovich's ideas with new tools. Researchers have developed computer simulations of Boscovichian systems, exploring the behavior of point particles interacting through various force laws. These simulations have shown that Boscovichian systems can exhibit a wide range of complex phenomena, including self-assembly, pattern formation, and emergent behavior. These studies provide new insights into the potential of Boscovich's theory for explaining the properties of matter. One might consider the implications of Boscovich's theory for the philosophy of science. His emphasis on a single, universal force law reflects a deep commitment to reductionism, the idea that all phenomena can be explained in terms of a small number of fundamental principles. Boscovich's theory represents an extreme form of reductionism, seeking to unify all of physics under a single law. This contrasts with more pluralistic approaches to science, which emphasize the importance of multiple levels of description and the irreducibility of certain phenomena. The historical trajectory of Boscovich's theory of natural philosophy offers a compelling case study in the evolution of scientific ideas. Initially met with skepticism and resistance, his ideas gradually gained influence, shaping the development of electromagnetism, atomic theory, and quantum mechanics. While Boscovich's specific theory may now hold sway in its original form, the underlying principles of force fields, reductionism, and the search for a unified description of nature continue to inspire scientists today. His work exemplifies a profound and audacious attempt to understand the fundamental nature of reality. In conclusion, Roger Joseph Boscovich's theory of natural philosophy stands as a landmark achievement in the history of science. His vision of a universe governed by a single, universal force law, mediated by point particles devoid of extension, represents a profound departure from the prevailing Newtonian worldview. While his ideas faced criticism and challenges, they profoundly influenced subsequent generations of scientists and philosophers, paving the way for the development of electromagnetism, atomic theory, and quantum mechanics. Boscovich's legacy lies in his bold attempt to unify all of physics under a single, elegant principle, a quest that continues to inspire scientists today. The theory's initial strangeness eventually proved to be an asset, as it challenged scientists to rethink assumptions about the nature of fundamental elements